Today's lesson is going to give a connection between entropy and spontaneity, and we're also going to talk about the second law of thermodynamics. We're still referencing chapter 16 in the textbook. So here's a real quick review of what we talked about in the last lesson. We talked about spontaneity and also entropy, and we said processes are spontaneous when they result in an increase in disorder, an increase in entropy. And nature always, always, always moves towards disorder. And we looked at that in terms of your bedroom. You may remember that example. So this actually leads us to the second law of thermodynamics, which says that in any spontaneous process, there's always an increase in the entropy of the universe. So this gives us our connection between entropy and spontaneity. So for any reaction to be spontaneous, the entropy of the universe must be positive. So your book gives this little equation. We never really do any math with this, but I do want to make you aware of it because we're going to be talking about entropy as far as it changing in the universe. And that means we're going to be looking at the entropy of systems and entropy of surroundings. And when we add those two together, the system and the surrounding entropies, the reaction will be spontaneous if delta S of the universe is positive or greater than 0. If S is negative, the process isn't spontaneous, but could be spontaneous in the opposite direction. So just keep that in mind. If it's not spontaneous in one direction, it may be spontaneous in the reverse direction. So heat flow is what actually determines entropy changes. And I'm going to use money as an analogy. Let's just say that I have $50 to give away. And one scenario is I give that $50 to a millionaire. Do you think that that $50 is going to mean a lot to a millionaire who has millions of dollars? No, it's not really going to mean that much to him or her because they already have a lot of money to spare. But what if I gave that same $50 to you, a student or a college student? It would probably make a lot more of an impact on you or a college student because most of you aren't millionaires and maybe you have little money, you have a little bit of money. So that $50 is definitely going to make a big impact on you. So let's just say I change that $50 to 50 joules. And we're going to look at what happens when, oh geez, I'm hitting all the wrong buttons. Okay. So what happens when I give that 50 joules to surroundings that are already really hot? So if I have a high temperature and I give 50 joules to something that has a high temperature, the molecules are already in rapid motion. So that 50 joules is not going to make much of a difference. So I'm just going to write that out for you. Not much is going to happen here. But if I'm looking at a system where I have a low temperature and I add 50 joules of heat, the molecules are in slower motion, but that 50 joules of heat is going to increase the entropy, the molecule motion, and it's going to cause a change in that system. So what I'm trying to say here is the magnitude of the entropy of a system, or the size of that entropy, is going to depend on the temperature at which the heat is transferred. So if I have 50 joules of heat being transferred and it's transferred to something that already has a high temperature, not much is going to happen. It's not going to change the entropy. But if I add it to a system that has a low temperature to begin with, it is going to change the entropy and it is going to increase it. It's going to make that atomic motion faster. There's two important characteristics of entropy changes that occur in the surroundings. The first says that the sign of delta S depends on heat flow. Heat flow means, is it going into the system or out of the system? So we're going to be talking about endo or exo and how this affects the surroundings. So if I have, in our first example, an exothermic reaction, I have heat flowing into the surroundings. So my surroundings are here, and I have heat flowing into the surroundings. That means that the motion of the molecules in the surroundings, when that heat is being released, is going to increase the entropy of the surroundings. That should make sense. Delta S will be positive, molecules are moving faster, and so we have a positive delta S. Now, if I look at an endothermic reaction where heat is being absorbed or heat is going into the system from the surroundings, that means my motion of molecules is going to decrease, and this is going to decrease the entropy of the surroundings, and so delta S of the surroundings is going to be negative. So that's one important characteristic, and on the next slide we're going to look at the second. So the second characteristic says that the size of the entropy of the surroundings depends on temperature, and that's what I was showing you with the endo and exo on a previous slide. So if the temperature of the surroundings is already high, like what I have drawn on the slide, that means that that heat that's going to be given off is not going to have much effect on the entropy of the surroundings. So the surroundings aren't going to have any increased entropy. They're probably just going to stay the same. But if the temperature is lower, I have lower temperature, then that heat will have an effect on the entropy of the surroundings. It's going to increase the entropy of the surroundings. So temperature definitely has an effect on the entropy. Not only the temperature of the surroundings, but also how much heat is being transferred. And there's a reaction that, an equation that goes along with this. And that equation says that delta S equals a negative delta H over T. So we're looking at heat being released and delta T. I'm sorry, I said delta T, I meant just the temperature. So here is where temperature kind of gets put in that equation. And since H consists of a sign, positive or negative, and a number, how much energy, and temperature is in Kelvin, why do I have a negative in front of this reaction? Why do I have this negative here? Well, let's talk about why we have that negative there. Delta H, the sign's dependent on the reaction of the system. And this equation is dealing with the surroundings. So basically, the negative changes the point of view from the system to the surroundings. What's going on with the entropy of the surroundings? If the reaction is exothermic, so I have a delta H, that's a negative, and heat is flowing to the surroundings, heat's going to the surroundings, the delta H or delta S of the surroundings should be positive when that happens. So I need to put that negative in front of delta H over T, because if delta H is negative, I want the surroundings to be positive, and the only way delta S can be positive is if I take the negative and then I have negative delta H. That's going to change that to a positive, and then I would show that my surroundings is positive. So again, the negative changes the point of view from the system, delta H of the system, to the entropy of the surroundings. So you need that negative there to change that point of view. I hope that makes sense. Now, before we do this sample exercise from your textbook, I want you to take a look at this reaction. It's a reaction of iron with an antimony sulfide, and it's producing an iron sulfide and antimony metal. And the reaction is exothermic. My delta H is negative 125 kilojoules. So when I think about the equation that I'm using, delta S of the surroundings is negative of the delta H over T, I should get a positive delta S, which is what I want because it's exothermic. The temperature is at 25 degrees C, and delta S of the surroundings, that entropy should be increasing because the temperature is increasing because I'm adding more heat to the surroundings. So remember that the temperature needs to be converted to Kelvin, so I need to add 273, so that gives me 298 K. And I'm going to plug in for delta H a negative 125 kilojoules, and I'm going to divide it by 298 K. And that's going to give me a delta S that is 0.419 kilojoules per Kelvin. Usually, though, we say delta S in terms of joules, so this would be 419 joules per K. And I believe that in your textbook, when we start to talk about standard entropy, those values are given to you in joules per K. So you just want to make sure that you're looking at your units because sometimes it'll be kilojoules, sometimes it'll be joules, and I think your textbook uses joules. Now again, note that the delta S is positive, which makes sense because the reaction is exothermic and heat's flowing to the surroundings, which is increasing the disorder of the surroundings. So it should make sense that we have a positive delta S of surroundings. So I just showed you one way that we can calculate delta S. And just like with delta H, there were different methods that we could use to calculate enthalpy. We have different methods that we can calculate the delta S of the surroundings. So just like enthalpy was a state function, meaning it doesn't matter how you got from point A to point B, the path doesn't matter, the end result will be the same. And I showed you the mountain analogy with that, where somebody goes straight up the side of the mountain versus going back and forth across the mountain. You still get to the top of the mountain, you just got there in a different path. Well, entropy is also a state function, and so it doesn't matter what path is taken to get to the end result. So that's why we can use these different methods. So we're going to use delta S, the standard state. So that's what that little degree symbol means. If you remember from delta H, we had that little degree symbol. So we're going to look at the entropy of reactions the same way that we did with enthalpy or delta H of reaction. We're just going to look things up in Appendix 4. We're going to get the numbers, and we're going to take the sum of the entropies of the products and subtract the enthalpies of the reactants, and we're going to get the answer. So it's very, very similar to calculating delta H's of reactions. Now to save time, your textbook, I took a picture of what was given in your textbook for this particular example, which gives you the standard entropy values in joules per K per mole. So you don't need to go to Appendix 4 for them, but you should take a look at Appendix 4, make sure you can find that delta or the entropy column, and notice that they are in joules per K per mole. Now, I'm going to show you the information that is going to be used. Now remember, the 2 means 2 moles. 3 means 3 moles. I'm not always going to write that, but I just want you to see it this time, that the entropy is 53 joules per K mole. And here's where the mole cancels, and I'm left with joules per K. So I also want you to take note that oxygen gas is not 0 like it is in enthalpy. It actually has a value. So I have 3 times 205 joules per K. And then sulfur dioxide, I have 2 at 248. And then I have nickel oxide, which is 2 times 38. Okay, so those are my values. And now I'm going to set up this delta S of reaction using the standard states again. Doesn't matter how we get to that final answer, just matters that we got there. So I can use this way of calculating, or I can use the negative delta H over T to calculate the S of the surroundings. So either way works. When I do all the math, I end up getting 76 plus 496 on this side. That's my products, and I'm going to subtract it by 106 plus 615. And when I do the math, I get negative 149, and this is joules per Kelvin. Now I got a negative delta S, and this actually should make sense. If you go back and you look at this reaction, I have my states of matter, solid and a gas on this side, gas and a solid on the product side. But if I look at the number of moles I have of my gas, they actually decreased. So I have decreased number of gas molecules, which means I have less disorder on the product side. So a negative value for delta S in this particular reaction makes sense because of the decrease of gas molecules. I want you to try this sample exercise on your own. I give you the standard entropies down in the bottom left corner of the screen, and you should be able to plug in the numbers and solve for delta S, and then check in your book to make sure that you have the correct answer with this one. Now this one's hard to tell and make a prediction because you have a solid going to a solid and you have gas molecules that are equal on the reactant and product side. So this one's going to be a little bit more challenging to try to make a prediction. So you'll have to see if you get positive or negative for the delta S for this one. So take a try at that one and then check in your textbook for the answer to see how you did. Now your assignment is pretty short tonight. It's pages 783 and 784. You're going to be doing numbers 25 and 26. I don't care if you put it in the Dropbox as a picture or a PDF, just make sure you handwrite the assignment. Hope you have a great day, guys, and I will see you on Friday when we talk about Gibbs free energy.